Okay, welcome to the last sound video of the year, which is all about sources of sound and where sound comes from. So, sound always starts with standing waves. And the easiest thing to visualize a standing wave with is a string that is fixed at both ends, just like the mechanical oscillator that we had set up on the teaching desk. So a standing wave occurs when a string is fixed at both ends. And in that case, only waves which are motionless at the ends of the strings can happen. So we force nodes to happen at both ends of the string. And that means that everything in between has to fall in line around that. So we can get one standing wave with one antinode that looks like this, or we can get a standing wave with two antinodes, or three, or 4, or 100, or whatever. The only key is the two ends have to stay fixed, and that is what determines the shape and therefore the frequency of these standing waves. The frequencies of a standing wave are called resonant frequencies. Remember, we talked about resonance as being a buildup of constructive interference at a frequency that an object really likes. So, when we fix both ends of a string like this, it has frequencies that it really likes to oscillate at. And those are the resonant frequencies. And we can also refer to them as harmonics. So, the most basic frequency you can get is this one. And we call this the first harmonic, or the fundamental. If we get a little more complicated than that, we get the second harmonic, or the first overtone. So if you're counting by harmonics, all you have to do is look at the number of antinodes you have. So the first harmonic has one antinode. The second harmonic has two antinodes. The third harmonic has three antinodes, and so on. If you're going to talk about overtones, overtones are however many steps up from the fundamental it is. So, the fundamental has one antinode, but the first overtone has two, because this is the first frequency we can get above the fundamental. It's the first one we can get over that for our overtones. Now, in order to figure out what kind of sound a given string will make, we can use some equations to find the wavelength and frequency. So to find the wavelength in any string, you take 2 times the length of the string and you divide by the harmonic. So if it's the first harmonic, we're going to put number 1 in for n. If it's the second harmonic, we put 2. If it's the third harmonic, we put 3, and so on. And this kind of makes sense, right? If we look at the wavelength for the second harmonic, it would be 2L over 2. So these cancel. So the wavelength ends up just being the length of the string. And that totally makes sense, because when you look at the second harmonic, that is one full wavelength, a full up and down. Now, for the first harmonic, the wavelength is going to be 2 times the length of the string, because to get one full wavelength, it would have to be double the size. This first harmonic is only half of a wavelength, so we would have to double that. There we go. Now, to find the frequency, we use our handy-dandy equation, V equals frequency times wavelength. V equals F lambda. All we did in this first step was we rearranged this equation to solve for frequency. Now, in order to get the second equation, we just took this and we substituted 2L over n in for frequency. So we get frequency is equal to the harmonic number times velocity over 2 times the length. And the last equation is telling us that when you want to find the frequency of a wave, all you do is multiply the fundamental by which harmonic it is. So if, let's say, you have a fundamental frequency, F1 is equal to 440 hertz. And I want to know what is F3. All you have to do is take 440 and multiply by 3, and you will find your answer. So let's do an example. What length must a guitar string be if the speed of sound in the string is 900 meters per second and you desire to produce a note with a frequency of 440 hertz? Well, we know the speed of the wave in that string, and we know the frequency. And we're trying to find the length of the string. So in order to do that, we have to first solve for the wavelength. So we know speed and we know frequency. To solve for wavelength, all we do is use V equals F lambda. We rearrange to solve for wavelength, so that is then velocity over frequency. So we take 900 and divide by 440, and we find that the wavelength of this string is 2.04 meters. Now, in order to find the length of the string, we know that the wavelength has to be 2 times that. Because, remember, our fundamental frequency only represents half of a wavelength. So, we have to then solve for L here, because that's what we're trying to find. And we find that L can be found by taking the wavelength and dividing by 2. We know the wavelength is 204 meters, because we used our V equals F lambda equation to solve for that. And we just divide that by 2. And we find out that the length of the string to produce a standing wave with a frequency of 440 hertz in this string has to be 1.02 meters long. Now, strings aren't the only things that make sounds. Musical instruments can be made out of vibrating strings, vibrating membranes, which is a drum, some kind of surface that vibrates, vibrating metal or wood shapes, and vibrating air columns. There are all kinds of different ways to make musical instruments. The key is to start a vibration in whatever that object is. And it can be started by plucking, like in a string, striking, like a drum, bowing, as in a violin or another string, or blowing, and this would be like a trumpet or a flute. And the vibrations are then transmitted to the air, which makes it resonate, and then it travels through the air to our ears. The strings on a guitar can be affected by shortening or lengthening the size of the string. So, in order to get a standing wave here, you first have to make it vibrate. You need to pluck it or strum it in some way. If you want the frequency to increase, what you do is you shorten the string. When you shorten the string, you are effectively shortening the wavelength, which means you are increasing the frequency. So the farther down this way on a guitar string you place your finger, the higher the frequency will be. But you've probably noticed that guitars have more than one string on them. They have 6 strings because the pitch of a string can be altered by the density. The thicker the string is, the lower the frequency it's going to be. A piano takes advantage of both length and density of the strings. And because it does this, it can cover more than 7 octaves. And an octave is 8 full notes. So the lower strings at the bottom of the piano are not only very, very, very long, they're also really thick. And this causes them to vibrate more slowly, so the frequency is going to be much lower. The ones at the top, up here, at the very high pitch end, are going to be really short and pretty thin. And this is going to help them vibrate very quickly to have a high frequency. Now, wind instruments create sound by making standing waves in air. So how do you do this? Well, with a tube that's open at both ends, like most wind instruments, it has what we call pressure nodes. And what this means is, let's say that this is the opening of the trumpet or saxophone or flute or whatever you're playing. When you blow into that instrument, you are making the air vibrate a lot. So you're going to have a displacement antinode there. Your air molecules there are going crazy. And because they're going crazy and moving around a whole lot, there's a lot of pressure at that point. So when we look at the pressure in the air at that point, that's like a node. Now, you can get different frequencies in the same column of air. Like we had with a standing wave in a string, the thing that determines what kind of frequency you have is that it's fixed at both ends. For this instrument, it's that at either end, the air is able to vibrate. So instead of having a node at either end, we have an antinode. But as you increase where the nodes are, and you do this by pressing buttons on the trumpet or the saxophone or whatever, you are forcing there to be nodes at specific places. And you have forced antinodes to be here, so the standing wave has to be created around that. Now, if the instrument was built such that there was a button here, it might not work. The buttons have to be placed in a very specific way so that the nodes happen right where they need to in order to create that standing wave. Now, we can also have a tube that's closed at one end, and some organ pipes are like this. And when this happens, we get our antinode at the end where the air is coming into the tube. But where the tube is closed, the air cannot vibrate. It's stuck where it is. So at that end, we have a node. So this looks very different from something that is open on both ends. And when we have closed pipes, it turns out they only have odd harmonics. And that's because we have an antinode at one end and a node at the other. And we can never have two nodes at the ends or two antinodes. We have to have one of each. And when this happens, we only have odd harmonics. We only have 1, 3, 5, 7, so on. And closed pipes are half as long as the same frequency open pipe. And this is why they use them in organ pipes. So an organ has to have some closed pipes and some open pipes in order to hit every harmonic. But when the pipes get much, much longer to hit the low frequency notes, it's to their advantage to use closed pipes because these only have to be half as long. They don't have to be as big as an open tube has to be. So to recap, if we have a string or an open pipe, to find the fundamental wavelength, which is this, or if it's an open tube, is this, you take 2 times the length to find this. For a closed pipe, to find the fundamental wavelength, which looks like this, you take 4 times the length because our closed tubes are half as long. Now, what makes an organ different from a trumpet, different from a flute? They all can play the same note, which technically is the same frequency, but they sound different. And the reason they sound different is because of superposition. Remember, it's when waves add together. So it happens that they sound different because of overtones. So if you look at these pictures, we have a frequency spectra, which means that each little spike you see in these graphs represents a frequency that exists when that instrument plays a note. All of these instruments are playing the same note. They're all playing this note right here. That's why it's the biggest peak. But if you notice, all of the other frequencies that show up are different for each instrument. And this is what causes them to sound different from each other. It's these overtones that show up naturally, and those will affect the tone of that instrument. So your homework for tonight is to answer these 3 questions. What length must an open tube be if the speed of sound in the tube is 750 meters per second, and you desire to produce a note with a frequency of 600 hertz? Number 2, how long would a closed tube need to be for the same information above? So use all the information from number 1 and find the length of a closed tube to have that happen. And 3, draw a standing wave with 5 nodes, including the ends. What harmonic is this, and what overtone is this? So do your best on these and have them ready to hand in the next time you come to class.